Welcome all again in this next lecture related to signals and systems. So our aim here in this lecture is to discuss about the LTI systems. See, in our earlier units, in our pre-discussions, we people have enough knowledge about what kind of different signals are there, what kind of different systems are there. Now, from this point onwards, our job of playing with those signals and systems will really start, and we'll start enjoying the mathematical treatment, the mathematical way of learning those signals and systems, right? So here in this unit, our focus will be towards analyzing the LTI systems, right? So obviously this word LTI is a very beautiful word. It's something, the heart of the signal processing, henceforth that is going to remain with us for lifelong, right? So what this LTI is, right? So LTI stands for linear time invariant systems. LTI stands for linear time invariance. It is LTI, right? So already both the words, those are there, those are included in this particular thing, are already known to us. That prerequisite knowledge regarding what is linearity and what is time invariance, both the things are there with us right now, right? Okay, so a beautiful combination of this linearity and time invariance is further going to give me another more beautiful concept of LTI system, right? Why I am calling it as beautiful, or why for me, for the entire signals and systems domain, this LTI is beautiful. Obviously, we are going to discuss that thing, right? So, let me talk about something about linearity, right? We are not considering any other system. We are right now not considering whether the system is static or dynamic. We are not considering whether the system is causal, non-causal, right? N number of different classifications were there. But right now we are focusing only on these two buzzwords, linearity and time invariance. Let us discuss why linearity is very important for any particular system. Our aim is to analyze the system. Based on its linearity and time invariance. So indeed we should know about why linearity is important and why time invariance is important. So first of all, let us talk about the importance of linearity. Tell me, why do you think linearity is important? You can very well comment in the comment section there, right? Or you can put your opinions on the discussion forum of Call. It's equally well. Right now, give yourself a minute and think about why linearity is important when we are concerned about a system. When we are concerned about a system. System is something which operates on the data. Already we have discussed that. Why linearity is important? Linearity is important. Why? Because that particular characteristic is going to make my system something which can be very predictable. I can judge something about the output that in turn is going to be there in my hand. So see, a system is developed according to the conditions that those are put forth by the users there, right? So conditions are put forth by the users, but at the same time there is some opinion regarding that system's output also. Okay, so indeed if I know how a system behaves, I can be very well in a position to determine the output. So that is particular predictability is very important characteristic, very important parameter regarding this linearity, right? So this linearity is something that says if proportionally I change my input, there is a corresponding proportional change in the output, weighted sum of inputs, right? That's what we have discussed about. So a linear combination of the inputs, let me talk about how it is going to give me the output. So as and on I play with the input, the same kind of change I will be able to see in the output. So that kind of predictability is the foremost important point regarding the linear systems, right? So if I press A, let me say that I am playing the piano. On that particular piano, I have a button A. If I press A, I will be hearing A. If I press B, I will be hearing B. Together, if I press A and B with the same thing, with the same modulation, I am going to listen A plus B sound, right? So that's what I can say, that the piano is a linear system, right? At the same time, proportionality, when I talk about proportionality, earlier I talked about this particular thing as a superposition kind of thing. Now when I talk about proportionality, weight, in that case, see, if a soft touch is there, the sound in turn I am going to hear about is a softer one. If I press that particular button hard, in a hard manner, obviously I am going to listen a stronger sound, a louder sound indeed, right? So that way, that proportionality also is a very, very important parameter when we talk about the linear systems. So the beauty of the linear systems is that those can be very, very predictable, right? So in real-time applications, when we want to develop a particular system there, obviously we want the output to be a predictable one, and hence we are focusing on the linear systems. Similar is the thing when we talk about the time invariant systems. What happens in this case is, see, today also if I switch on this light, it is working properly, provided that all other conditions are stable. I'm not talking about the random conditions or the component degradation, something like that. I say that the situations are ideal. If I switch on this button today, that is going to give me the same amount of in a very non-technical manner I am talking right now. The same light I am going to come across. Tomorrow also if I switch on that button, the performance will be same. Rather, see here the system's performance, it is predictable. It is predictable. Now let us talk about time invariance. Let me say that I am playing with a washing machine. I am just working out, so operating that washing machine. What I do is I press the button of start right now. I am going to start that wash cycle at the very instant. But there are programs wherein I can set that delay. After that delay elapses, again the wash cycle starts, right? So is there any difference in the working condition when I press the button start right now and start that wash cycle, and if I press that start button after a certain instant and I start the wash cycle? Both the operation at both the instances of time, before the application of the delay and after the application of the delay also, the performance of the system is going to remain very, very same, right? So that means the operation that the system is carrying out on the data, it is entirely time invariant, right? That too also, here also the predictability is playing a role. Am I right? So that way, when I use this particular combination of linearity and time invariance, obviously I am going to make my systems to be a predictable kind of thing, right? So that's why there is a need to study the LTI systems, right? Second thing, see, okay, now we are well convinced why to use the LTI systems. See, now let us try to put forth, if we use the LTI systems, what kind of benefits we are going to take, we are going to have in terms of its mathematical representation and in terms of its technical form, right? Technical implementation rather. Okay, so there are various what I can say benefits associated with that LTI system there. See, the foremost thing that this combo of LTI is going to give me is these systems can be modeled accurately. These systems can be modeled accurately as these work in a proportional manner of input-output relationship. Obviously, a mathematical model for those systems can be very well developed. So, that modeling can be accurately done. Time invariance also is going to give me the firm behavior, the very correct behavior of the system. So, obviously, we can very well develop the model for that system. Now, that mathematical model that we can develop using the predictable nature of the systems is in turn going to help us towards developing the algorithms for those kind of systems. And obviously we are working in the era of DSP, we are working in the era of VLSI. This particular algorithm kind of thing is the heart of anything. You develop the algorithm, you program the thing, you dump it on the chip and you get your work done. That's what was happening with my washing machine also, right? So mathematical models are in turn can be very well what I can say, process in terms of their algorithms, and those algorithms can be very well implemented on any kind of processor there, right? Similarly, there what happens in case of this LTI systems is there is linearity. There is linearity. We can very well add small components together. Linearity superposition, wherein we were adding small chunks, right? Now those small components can be very well added together, and the cumulative response can be obtained. Right? So if I want to process a complex signal there, that complex signal also can be very well chopped down, or we can say that it can be very well cut down into smaller components, and those smaller components further can be very well added together to see the cumulative response indeed, right? So that's what this particular thing is again going to make my LTI systems a beautiful tool for me. Secondly, one or something that we have to focus at this instant is but obvious question can be thrown to me ki ma'am, if you are talking about linear time invariant system, aren't there any others? There are many signals in nature which are by themselves are non-linear, right? So that is a but obvious question. How to handle those things using these LTI systems? Are our LTI systems going to fail in that case? No. LTI systems, that's why I always say that the systems are beautiful. If a particular non-linear signal also is there, let me say that such kind of non-linear signal is there, any non-linear signal, if observed for a smaller period of time, it seems to be linear. Yes, this signal seems to be linear. So model this small part using linearity principle, further using superposition, add those parts together and get your output. So that's how non-linear signals also are developed, are cut down into smaller chunks and further added together to give the cumulative response. So this is how, once we know how the LTI systems behave, how to analyze these LTI systems, obviously we'll be able to model different kind of or different types of systems. Those are available right now. So this is all about the LTI systems, and in the next session we'll be discussing about a very beautiful component that will help me to analyze that LTI system. So we will call it for this session. Thank you.